right, we're going to do 3.10, which is some more optimization problems today. Let's look at number 1. A rectangle is to be inscribed in a semicircle of radius 2. What is the largest area the rectangle can have, and what are its dimensions? All right, so we're going to start by drawing a graph. We have a semicircle, meaning a half circle, radius of 2. Okay, and then we have inscribed in that a rectangle. All right, so let's see if I can make this even. Okay. So the key to this is that where this rectangle hits the circle, we kind of want to talk about that point for a second. So this would be the point X for the X value, and then the Y value is the point on the circle, right? So let's think about the equation of this circle. The circle, that would have an equation of x squared plus y squared equals 4, since it's a radius 2 circle. So let's solve for the y value there. So we're going to minus the x squared and then take the square root. Okay, so we know our y value here would be the square root of 4 minus x squared. Okay, so we're trying to maximize the area of this rectangle. So the area of a rectangle is length times width. And then here, let's talk about our rectangle that we have over here. So our length would be from here to here. So that would be 2x. Because it's x to the left and x to the right. And then our width from here to here is just how high up the y is. So that's going to be radical 4 minus x squared. All right, so in order to maximize the area, we want to take our derivative and set it equal to 0. This is a times, by the way. You guys know I can't do dots very well on here. Okay, so we're going to do product rule here for our derivative. So we have a prime equals derivative of the first times the second plus derivative of the second. So this is chain rule times the first. Okay. All right, so let's simplify this a little bit. We're setting it equal to 0. I'm just going to simplify this second part. So we have the 1/2 and the 2 that can cancel. Okay. So that gives us a negative 2x squared over radical 4 minus x squared. I'm going to add that negative part over to the left. So I have 2x squared over radical 4 minus x squared equals 2 radical 4 minus x squared. My 2's can cancel out because I have 1 on each side. And then I can cross multiply and I get x squared equals 4 minus x squared because the radicals cancel. If I add the x squared over to the left, that's going to give me 2x squared equals 4. Divide by 2. Take a square root. Okay. So now we're going to write down our answer. So our final answer are dimensions of our rectangle. So I'll write that right here. Rectangle dimensions. I know that my x value is going to be 2 radical 2, because remember the x goes to the left and the right for the length of the rectangle. And my height is going to be 4 minus x squared. So 4 minus 2 is 2, and then square root of that. Okay, so just to clear that up really quick, I was just plugging in my x value into here, and then remember that the length, I have to double it because it's the x value to the left and the right of 0. Okay. The last question was, what is the largest area? So that means I actually want to plug in my x value into my area formula. So 2 radical 2 times radical 4 minus radical 2 squared. So 2 radical 2 times radical 2, 2 times 2, which is 4. All right, go ahead and pause it if you need more time, and then we will move on to number 2. Okay, number 2 says the U.S. Postal Service will accept a box for domestic shipment only if the sum of its length and girth or distance around does not exceed 108 inches. What dimensions will give a box with a square end the largest possible volume? Okay, so we want to start by drawing a box. And I did notice it said a square end, so I'm going to go ahead and make my end x by x. And then my length here, I'm just going to make it y. All right, so it says that they want the length and the girth to not exceed 108. So that would be y would be the length plus the girth, meaning all the way around, would be x plus x plus x plus x. So that would be 4x. Okay, and then not exceeding 108, I'm just going to say equals 108 because I want to make this as large as possible if I'm trying to maximize the volume. All right, so I'm going to solve this for y. 108 minus 4x. Good. Okay, now I'm going to go ahead and write my volume formula. Length times width times height. So I have my length y times x, so x squared. And then I'm going to go ahead and plug in my 108 minus 4x for the y. Go ahead and distribute the x squared. Okay. Now I'm trying to maximize my volume, so I'm going to take the derivative and set it equal to 0. So this gives me 216x minus 12x squared. Set that equal to 0. All right, I'm going to factor out a 12x. So I get 18 minus x. So my two solutions are x equals, oops, I don't quite have enough room down there. So I'm going to go over here. All right, so I have x equals 0 and x equals 18. Obviously, I'm going to reject the 0 because that isn't a box if it has a 0 length. So I'm going to reject that one. So that means my only answer is 18. They want the dimensions of the box. Okay, so I know the 18. I just need to figure out the y. So that's going to be 108 minus 4 times 18, which if I do that out gives me 36. So my dimensions of my box are 18 by 18 by 36. All right, let's go to number 3. So on number 3, it says the 8-foot wall shown here stands 27 feet from the building. Find the length of the shortest straight beam that will reach to the side of the building from the ground outside the wall. All right, I'm just going to say it right now. I did not give you guys enough room on this. When I did this problem out on a paper using a pen, writing my normal size, it took up an entire sheet of paper. So you might want to pause the video, go grab a blank sheet of paper. We'll do the problem on a separate sheet, and you can just staple it to your notes or put it into your binder. All right, so we have a lot of different unknowns here because depending on the length of the beam, two things are going to change. So the beam length obviously is one thing that can change. I'm going to label that L for length. Depending on the length of the beam, it's going to reach a different distance away from the wall here, X. And then it's also going to have a different height on the wall where it touches, so H. Okay, so we have three things, three variables that can change here. I can just take a wild guess, and I'm probably going to be using similar triangles here because I have these two inscribed triangles that are similar. And I think that's going to be important because when I have three variables, that's a bit of an issue, and I kind of want to eliminate one of the variables so that I'm working in two variables instead of three. All right, so we're going to use our similar triangles for that. So we have this triangle right here, the little one, and then we have this triangle right here, the big one. Okay. All right, so the little triangle, I have 8 over x. The big triangle, I have h over x plus 27. And now what I can do is multiply both sides by x plus 27. And that gives me something I can plug in to replace the letter h. All right, so now we're going to use Pythagorean theorem to relate our variables here. So we have this bottom side right here. Okay, x plus 27 squared plus my height h squared equals the length of my beam L squared. And then remember what I said, we want to replace the h. So we're going to have x plus 27 squared plus, this is going to be 64 over x squared. I'm squaring that right away. And then x plus 27 squared. Okay. Next, I think I want to go ahead and factor out an x plus 27 squared. Okay, so that gives me now 1 plus 64 over x squared. Okay, and then one other thing I want to do is I want to factor out this x squared. I kind of want to bring it out. So in order to do that, it means I also have to take an x squared off of this. Since it doesn't have an x squared, it means I have to like make it x squared over x squared, right? Since it's equal to 1. Okay, so I'm just going to do this. So this would become x squared plus 64, and then a 1 over x squared on the outside. And so you'll notice if I did distribute that in, the 1 over x squared and the x squared would cancel to be 1. All right, so the reason that I want to do that is because now I can do a square root of both sides. And on the left, I have just x plus 27 because the squared gets canceled. I have square root of x squared plus 64, and then my other 1 over x squared, the square cancels on that as well. So just 1 over x. Okay. So remember, I'm trying to minimize the length of the beam L. So now I'm going to do my derivative. Let's actually, I'm going to do one more step before we do that. Right now, see how I have 3 different things timesing? I have the x plus 27, I have the radical x squared plus 64, and I have the 1 over x. What if I bring in this 1 over x? I'm going to bring that in here because now I would just have 1 plus 27 over x. All right, now when I do my derivative, I only have 2 things, okay? So this is going to be product rule. All right, I'm going to bring my derivative over here. Oh, I don't think I'm going to have room. Okay. I'll do my best. Okay, so L prime. Okay, so this is product rule. So I have derivative of the first, which is 1 plus 27 over x. Think of it as 1 plus 27x to the negative 1. So that gives me negative 27x to the negative 2 times the second plus derivative of the second, this is chain rule, times the first. Okay. All right, let's try to simplify some things here. So some things I'm noticing, I have a 1/2 and a 2. I know those can cancel. Okay, all right. So L prime equals, I'm going to put this x squared on the bottom. Okay, over here, the x squared plus 64 to the negative 1/2, that also goes on the bottom. So it's a radical x squared plus 64. And then this x right here, I'm going to distribute it into this parenthesis right here. And so that is going to give me x plus 27 right here on the top. Okay, let's add this negative 27 stuff here in the front. Let's add it over to the other side. Remember, we want this equal to 0 because we're trying to minimize the length of the beam. So add that over. So I get 27 radical x squared plus 64 over x squared equals x plus 27 over x squared radical plus 64. I'm going to go ahead and cross multiply. Okay, so that is going to give me 27 times x squared plus 64, right? Because the radicals have canceled. Oops. Equals x squared times x plus 27. Okay, distributing, I'm going to get 27x squared plus 1728 equals x cubed plus 27x squared. If I minus 27x squared, those are going to cancel. So I get 1728 equals x cubed, and I do my cube root, and it is 12. All right, so clearly our algebra skills have to be pretty tight. We really are focusing a lot on solving equations and doing correct steps when dealing with all these crazy algebraic expressions. All right, let's go ahead and answer the question. The question is the length of the shortest beam. Okay, so I am going back to the length of the beam, which is right here. And I am plugging in my value for x that I got, which was 12. Okay, and at this point you can go ahead and plug that into your calculator, and when you do the shortest length of the beam, it gives you 46.87. All right, go ahead and pause it if you're still writing, and we're going to try number 4. Okay, number 4, another one where I think you can fit it in this space if you write small. It's not, I don't think it's as long as number 3, but if you would feel more comfortable having a separate sheet of paper, being able to spread your work out, then you can do that. Okay, so number 4 says a silo, base not included, is to be constructed in the form of a cylinder surmounted by a hemisphere. The cost of construction per square unit surface area is twice as great for the hemisphere as it is for the cylindrical sidewall. Determine the dimensions to be used if the volume is 8,000 thirds pi cubic feet and the cost of construction is to be kept at a minimum. Okay, so I'm going to go ahead and draw my picture. Everybody should know what a silo looks like. So there's my cylinder surmounted by a hemisphere, half sphere. All right, so what are my dimensions here? Well, I'm going to have the height of the silo, the cylindrical part, and then the other thing that is unknown is the radius of the top. Okay. Remember that the top is 2 times the cost of the bottom for the materials. Okay. And the other thing that we know is that the volume of this is 8,000 thirds pi. Okay, let's start by writing down the cost of the materials. So the materials, when I'm talking about cost of materials for this, I'm really looking at surface area, because whatever we make this out of, we're going to need to find the amount of area needed to cover this shape, okay? So our surface area is cut into 2 sections here. So we have the first section, which is this cylindrical part. Okay, so that's going to unroll as a rectangle. It's going to have a height of h, and it's going to have a length of the circumference of the top, which is 2 pi r. Okay, the second part is the surface area of the hemisphere. Okay, so I'm going to take that. And so that is the half sphere. Okay. So I had to Google that one, and the surface area of a sphere is 4 pi r squared. This is a half of a sphere, so I'm going to divide it by 2. But the cost for this part is twice as much as the other one, so I'm actually going to times it by 2, and those things cancel. Okay. All right, so let's write our cost equation now. So the cost of this is going to be the area of the cylindrical part, which is 2 pi rh, because it's the area of the rectangle that we drew there in orange, plus the surface area of the sphere, 4 pi r squared. Okay, so now we're going to move over to the volume section. The reason the volume is important is because when I plug the h and the r into the volume, it's going to allow me to isolate one of the variables, so that instead of having 2 variables in my cost equation, I only have 1. Okay, so let's think about the volume of this. So we have the volume of the cylinder, which is pi r squared h, plus the volume of the half sphere. Volume of a sphere is 4/3 pi r cubed. Half would be 2/3 pi r cubed. Okay, and I know that this is equal to 8,000 thirds pi. Okay. One thing that's nice about this, if you notice, every single thing has a pi, so I could cancel pi, pi, pi. Like if I divided everything by pi, that's what I would get. Okay. All right, so now let's isolate the letter h, and that's going to allow us to replace the h with an expression involving r. Okay, so I'm going to minus over the 2/3 r cubed first. So 8,000 thirds minus 2/3 r cubed. And now I can divide everything by r squared. So h equals 8,000 over 3r squared. Since I'm dividing it, it goes on the bottom. Minus 2/3 r cubed divided by r squared is just r. All right, I'm plugging that into my cost. So now I have c equals 2 pi r times this crazy expression plus 4 pi r squared. All right, I'm going to go ahead and distribute the 2 pi r. So I get 16,000, that's 8,000 times 2. Pi, the r on the top is going to cancel with one of the r's on the bottom. So I get 3r on the bottom minus 4/3 pi r squared plus 4 pi r squared. All right, I can actually combine the -4/3 and the 4. So I'm going to do that. I'm going to actually erase to save myself a little bit of room. So 4 minus 1 1/3 is 2 2/3. Okay. 2 2/3 is 8/3. Okay, I'm ready to try to minimize my cost. So to do that, I'm going to do my derivative of the cost and set it equal to 0. So the first part, I want to think of it as 16,000 pi over 3, and then r to the -1. So this would give me negative 16,000 pi over 3r squared, right? The -1 becomes a -2, which means down the bottom, plus 16/3 pi r. Okay, I am setting this equal to 0. So now I'm going to add over the 16,000 pi over 3r squared. 16,000 pi over 3r squared equals 16/3 pi r. And what seemed like it was going to be an absolutely horrible thing to solve is proving to be pretty easy, because if you look here, if I divide both sides by pi, my pi is gone. If I times both sides by 3, my 3 is gone. If I times both sides by r squared, I would get r cubed divide by 16, I get 1,000. And then the cubed root of 1,000 is 10. All right, sweet. So my radius is 10. I'm going to come right back up here. I'm going to find my height by plugging in 10 into this equation that I solved for h. I'm going to keep it in orange. Why not? Okay, so I'm going to have h equals 10 squared is 100, so the bottom is 300. If I cancel 2 zeros, I get 80/3 minus 2/3 times 10 is 20/3. So this is 60/3, which is 20. And those are my answers. It said determine the dimensions to be used. Done.